Okay, good afternoon, everyone. If we could get underway. We have a lot to get through in this session. Very briefly, I'm John Walker. I'm from the UK Foreign Commonwealth Office. I'm also the Joint Task Leader for the OSI Operational Manual. That's enough introduction about me. You can read about me on the app. Talking about the app, you're encouraged to make use of it to vote for your favourite presentations and posters, so please avail yourself of that facility. So without any further admin from me, let's crack straight away with the first presentation. That's from Josephat Mulwa from the Department of Geology, University of Nairobi, Kenya. He's going to present a rapid and non-destructive method for determining in situ uniaxial compressive strength of rocks during on-site inspections. Each speaker has 15 minutes, but as we have one speaker has dropped out, we now have 18 minutes per session. So I would ask all speakers to stick to the limit, and hopefully we can have some questions from the floor. If you want to ask a question, please describe who you are and where you're from, and please use the microphones as this is being recorded and transmitted.
Okay, thank you very much. My name's Josephat Mulwa. I'm from the University of Nairobi, Department of Geology. So what I want to present to you today is a rapid and non-destructive method for determining in situ uniaxial compressive strength of rocks during an on-site inspection. So the keywords here are rapid, non-destructive, UCS, or uniaxial compressive strength, and OSIs. So a bit of introduction. The on-site inspection action plan serves as a tool for furthering OSI capabilities towards the establishment of a balanced, coherent, and robust verification regime at entry into force of the CTBT. And the OSI action plan overarching priorities include, among others, so these are not the only ones, further development and consolidation of inspection activities and techniques, and continued development of OSI equipment list with a view to having a near final draft list ready for consideration and approval at the first session of the Conference of State Parties. So in furtherance to the OSI action plan priorities or objectives, an experts meeting was held in Vienna International Center from 7th to 9th of March 2018. And basically the objective or the aim of the meeting was to consider specific issues related to ground-based visual observation and position finding. So during the meeting, Petrography Technique was proposed as an initial period ground-based visual observation technique. However, this technique was not recommended because of a number of reasons. And the first one was because it was considered intrusive. So you can imagine you are in the first phase of on-site inspection and you are negotiating with the ISP whether to collect rock samples and so on and so forth. Is it worth it? So that's the issue. So we wouldn't want a technique whereby you are in the initial phase and it becomes intrusive. And then the second one, it was considered to be destructive because if you collect a rock sample, then you have to subject it, you have to cut it, you have to prepare thin sections so as to examine its characteristics. And then thirdly, it was considered to be rather expensive in terms of human resource and finances, as well as time consuming. So it will take a bit of time to prepare a thin section for petrographic analysis. Additionally, this technique may not offer immediate results to allow other OSI activities and techniques to be undertaken, such as continued period techniques. So remember the objective of visual observation. We want a situation whereby we can pinpoint specific search zones where to recommend other techniques to be undertaken. So as an alternative, a Schmid-Hammer test method was proposed as an alternative to petrography technique. And so what is SME-DAMA test method? Now, SME-DAMA test method is also known as rebound DAMA test method. It is a non-destructive method. It makes use of a SME-DAMA, or what we call rebound DAMA device. SME-DAMA was developed primarily for testing concrete structures. Nevertheless, it has established itself as a recognized instrument for on-site, for in-situ rocks in the field. So what does it measure? Basically, it measures what we call a rebound number, and then you can convert the rebound number to uniaxial or unconfined compressive strength using calibration curves or linear or exponential correlations. And so once you convert the rebound number to uniaxial compressive strength, you get some information about the characteristics of the rocks in situ. Now, secondly, the method preserves the integrity of the samples, so no cutting is involved. It is relatively simple, so anyone in the inspection team can undertake a SME-DAMA test in the field. It is economical, it is versatile compared to most conventional crushing techniques, including rock cutting and thin section preparation. So this is the SME-DAMA device, and its operation and working is described in a number of manuals and procedures. So it's a very simple gadget, and it can be handled by anyone in the inspection team. So the next question to ask ourselves is, why uniaxial compressive strength determination? And so the answer to that is, the only tool available to the inspection team during an on-site inspection is a geological hammer. Now, geological hammer can only give you a qualitative indication of the characteristics of rocks in the field. Now, if we want a situation whereby we can get some quantitative information about the characteristics of the rock, then that will be an added advantage to the whole OSI inspection process. And SME-DAMA offers us that quantitative information to determine the characteristics of in-situ rocks in the field. So I want to present you some case study where we conducted SME-DAMA test. So the tests were conducted as part of a multidisciplinary study involving electrical resistivity tomography, multi-channel analysis of surface waves, drilling, geological mapping at a proposed Karula hydroelectric power plant tunnel route. And this one is located about 200 kilometers northeast of the city of Nairobi in Kenya. Now, for those of you who are conversant with IMS network, the location of this study area has no relationship to the infrasound station in Kenya, whose site location is also called Karura. So this is a site which is quite far from the city of Nairobi. So the proposed hydroelectric power plant tunnel route stretches over a distance of about 9 kilometers east of northeast of an existing hydroelectric power plant. And the intention is to use run of river water, which is estimated to be about 190 cubic meters of discharge from this existing hydroelectric power plant to serve the new power plant, which is the Karura hydroelectric power plant. And the proposed power plant will further exploit residual head between two reservoirs, that is Kindaruma and Kembere in the Upper Tana River Basin. So this is basically the location of the study area. So this is one of the reservoirs existing, and this is the other one, Kembere. And the red line shows the location of the tunnel. So obviously, because of environmental reasons, the power company didn't want a situation whereby they have to construct another reservoir. So what they wanted to do is to use the discharge water from this power plant and channel it through a tunnel to serve the proposed power plant. So we conducted Schmid-Dammer tests, of course, in addition to other tests. And I want to present to you some results now. So this is a geological map of the study area. And what we see is that the study area is basically made up of metamorphic rocks. Most of them are of Precambrian age, late Archean, early Proterozoic. And so the values show Schmid-Dammer test results in megapascals. And so the diagram to your right is a plot of the variations of the Schmid-Dammer test results in megapascals. Obviously, this data is skewed. It's not one of the best to do a contour map, but obviously the contour map is what the managers would understand. And that's why we plotted the contour map just to show the variation of the uniaxial compressive strength of rocks. And so this table summarizes the UCS values for different rocks. And so we can see a very great variation. And what we note here is that the uniaxial compressive strength of rocks in the study area is dependent on a number of factors. And one of those factors is the rock type. And then the second factor is degree of weathering. And then the third one, and which is of significance for on-site inspection, is macro and micro fractures. Because if you have an area where a UNE or a nuclear explosion has been conducted, obviously you would expect rocks to be fractured both on macro scale as well as micro scale. So we believe this is a very good method, which is easy. It is very convenient for everyone in the inspection team to conduct. Nothing much involved, and it is cheap, and so it adds value to the whole inspection exercise. So thank you very much.
Thank you very much indeed, Josephine, and thank you very much for sticking to time. Does anyone have a question? No, I don't see any. So let's move to the next presentation, please. Okay. Next presentation on the list is chaos during an on-site inspection, applying measurement restrictions to sample characterization at the base of operations. Rich Britton from the Atomic Weapons Establishment, Aldermaston. I think it's a very unfortunate acronym, chaos, because I'm quite sure that my colleagues in the OSI division are not about having chaos during an OSI, so maybe you want to find a new acronym. Rich?
Unfortunately, it's already published, so that's
oh, well,
possible.
You heard it here first, chaos in an OSI. Rich?
Cheers. Okay, yeah, so I'm Rich Britton from the UK. This is a stream of work that myself and actually Davies have put together. It was part of an uplift project a few years ago now. This sort of is the final rounding off of our prototype version. We expect this to be taken forward and developed and maybe made operational really for an OSI. But we've gone as far as we can in terms of the science, and that's what I want to present today. So, a very, very brief introduction to chaos. We are limited on time. It's the coincidence-based high-resolution analysis for OSI spectrometry. And I'll apologise only once for the name because I quite like it. Our main goal is to have a very easy-to-use system, a very automated system. An OSI is complex. It is a slightly chaotic environment. There's very highly trained people, but there's a lot of things that need to come together and work well. And so anything that's automated and easy to use is really key. And that's kind of the ethos behind this. We've looked at some other measurement restriction systems which are out there, which are being tested. So we know ofOn-Site from Israel has a system which looks very good. We know Osiris from the US, that's a more commercial system. And we think this can work in parallel with those. So a little bit of treaty text, I'll mostly skip over this, but just to say that it is in the treaty, and this is something that hasn't really been exercised. There's been lots of build-up events in IFEs, so far, but measurement restrictions has not really been tested, especially at the base of operations. This is something that needs to happen next time, I think. A little bit of rationale. This is some of the things we think a measurement restriction system should provide. The obvious things like calibration and reporting of status, hardware health, that sort of thing. The key thing I want you to take away is minimizing this probability of false positives and false negative detections. And also the open source nature of it. We think the ISP is going to want to inspect every single line of code. I know we would. So it needs to be open, it needs to be available. And what we come up with actually in the end when we're thinking through all these different the different things we need to incorporate in this system is that actually in the end it needs to be automated. And there's a number of issues with this, and Chaos was designed specifically to actually address some of these. So it's a little difficult because we don't actually know what level of measurement restrictions are going to be needed or required. So we've gone with the approach of tackling everything from 0 measurement restrictions right through to the inspector can't see any spectra, can only see a very simple traffic light system where there is no OSI relevant radionuclide or there isn't. And as an example, we think an ISP could turn around and say, actually, we have sensitivities that we don't want you to measure, and you can't measure any actinide signatures. And I didn't do the donkey work for this. My colleague Ash did. I thank him for that, because he went through all of the actinide signatures and looked at all of those regions. And if you restrict your spectra to just looking at those that aren't where an actinide is, you don't have a spectra. You have nothing left. So automation is key. Having said that, automation doesn't usually work that well. This is quite an extreme scenario. We had a lot of fresh fission products that we had on various samples, and we analysed about 250 and did a bit of a look back through some of our old data sets, and we found that at least 10% of the time we were misidentifying peaks in an automated solution, which then an analyst would have to go through and correct. And that's not really acceptable during an OSI. The spectra you see during an OSI would hopefully be slightly less complex than this. But there are still interferences such as iodines and other things that make it automated solution very difficult. So some of the solutions so far presented a windowed solution, where you, as I said, if we pretend that they do allow you to see some of the spectra, you can look at these windows, and you can look to see if there's no OSI relevant radionuclide. Now, some of these, they overlap with sensitive signatures. You might want to say you can't measure uranium. It rules out certain things. And even in a windowed solution, you're looking in a window and perhaps you see a peak, perhaps you don't. But with enough windows, you can reconstruct the Compton continuum, and you could go back and you could probably glean some sensitive information that you're not supposed to see. At 1 MeV, 80% of your signal is actually in the Compton continuum. And so we're not convinced a window solution would be acceptable to an ISP. So our solution, Chaos, is to just analyze everything. I mean, we've been developing coincidence systems at GBL 15, and we put a lot of time into understanding these signatures and quantifying them and characterizing them. And so we leveraged that and said, well, if we implemented a coincidence system at the base of operations, we could measure a few of these in coincidence, the ones in green. The ones in red don't have a viable coincidence signature for this system, but we can do it in anti-coincidence. And then we can do the traditional analysis at the same time. Everything would be list-moded, time-stamped, so we can go and replay the experiment. And so that sort of holistic solution, I hate that word, but where you bring together all these different analysis streams to improve your confidence is really what chaos is. So we were looking actually to build something. We thought, well, we'll build an MCA that can do this. And we would take McKayan, an electronics supplier, and they actually had something in the pipeline already. So they had this hexagon unit. And it's a dual-channel MCA for germanium detectors. And crucially, it's got a small embedded computer within the MCA that you can load software on, you can do other bits. So we could put the entire system in this really quite small MCA. It's the size of a small book. And it could do everything from the collection to the processing to the analysis to the reporting of all the data, which has obvious benefits for a measurement restriction system. So we've done lots of validation, and yeah, we validate the science for other purposes, for other reasons in our lab. And we've done some full-scale testing, which I'll come on to later, but we've done the validation. We've been doing our PTEs in the laboratory measurements for years now, via coincidence, as well as during a traditional way. So the science is validated. This was really a project in putting all those complex analyses and algorithms together in one unit. So it's an engineering task, really. So here's a sort of functional diagram what it would look like. You have a couple of ruggedized detectors. They would sit at the base of operations, and they both plug into this very brightly colored unit, and you connect to that via an Ethernet cable, and it's very easy to report back and to get information on what's actually detected and what isn't. This is kind of crucial for us. We're not software engineers, we're scientists, but we've built a thing to be modular and to have a bit of a firewall. So there is a user GUI, which is kind of this side, and that's how the user interacts with it. That's your Ethernet cable there, down the middle, and then everything else happens inside the unit itself. So at no point can the inspector get any information that isn't already approved prior to the inspection. So that's what it looks like in real life. Inside you can see there's a couple of HV units there. We've got a signal input. And this is the board. So it's like a Raspberry Pi. It's a BeagleBone. It's a different brand. But really easy to develop for, actually, and implement everything on. So there are no commercial solutions or tools for processing this kind of data, looking at coincidence stuff. It's all very much a research, lab-based effort at the moment. But as I said, we've been doing this for a few years now, and we worked actually quite hard to package this and make it very efficient to run on really what is a tiny computer, but it's pretty powerful. And just, it produces everything. We have the raw spectra, we have coincidence spectra, we have anti-coincidence spectra, and it's all done in real time and analysed in real time. And this is all done on it's a 1 gigahertz processor, which is quite incredible, really. And actually, I'll go back just because the bottom point there is having these 4 analysis streams. So you don't just have your 1 automated answer, you have 4 automated answers. And so that's where you start to build the confidence. Very quick example, this is what the actual interface looks like. It's just a simple Python Qt-based GUI. And there's some extra functionality for us testing and deploying stuff, but in this prototype, there are 4 buttons that an inspector needs to care about. There's start, there's stop, there's calibrate, and there's analyze. And that's all they need to do. Here's an example of a calibration. You get a very simple, it passed or it didn't. There's some yellow ones here where we had a fairly weak source and we didn't want to wait, but also it kind of shows the difference there. Here's some detailed analysis where you actually get the activity concentrations for each analysis stream. You get standard, coincidence, anti-coincidence, and windowed as well. We actually implemented that. Here's a more restricted summary where I was talking about that traffic light system. And you can see there, I think, hopefully, there is one green where 134, Cesium 134 wasn't present in this sample, and everything else was. But there are some yellows there where it wasn't confirmed yet, because it was only detected by one analysis stream and not the others. And that was just a function of count time. So in full restriction mode, we're thinking this is pretty much what you'll get. And these traffic lights at the moment are based on what, we've termed it a confidence factor, but really this will probably be part of the negotiation where you say what's restricted and what you can do, then also how you want to weight the confidence factor. And so at the moment, we've got these numbers that seem to work very well, where you get a positive increment for an analysis stream detecting something, and you get a negative increment for if it doesn't. And so you add these up, and you get a very simple traffic light system that's actually really robust. It's a very simple solution. We've done lots of full system testing as well as validating all the individual science pieces. And I won't go through all the samples, but the takeaway message here is over all these samples and hundreds of nuclides, we only detect the OSI relevant ones, and we report on nothing else. So a quick summary, all the science has been validated and published, and there's some references there for you. We've worked really hard on actually automating the whole thing and the analysis and the processing and everything else, which anyone that works with gamma spec and coincidence data they'll realize there's a lot of work there. It's designed for a range of restrictions, and you can pick and choose how you want to implement those. Easy to configure, and it's all open source. It's all there. You can read every line of code. You can go through it. We think there'll be some sort of software checksum that you could do to verify that the code hasn't been tampered with before deployment. And last but not least, there is a user-friendly GUI for inspectors, because they've got enough to worry about and they don't need a stressful analysis process. Some additional applications. This multiple analysis stream is pretty unique. We've not seen this before. Automated coincidence process, and again, that was really hard work, and we're quite proud of that. And you could automate this, put it in batch mode. It's all Python scripts at the end of the day, so you can make it do whatever you want. And we're happy to sort of share that and release with the PTS, which we are in the process of doing now. So finally, as I earlier mentioned, actually this was published last week. I was quite glad it got out in time for SnT. There's a link there that you can follow. I think it's actually free to download for 50 days, so if you're interested, get in quite quickly. And thanks really to our suppliers and our funders. I mean, Canberra were big on allowing us to implement our analysis algorithms. KM were great with the hardware, and ultimately all our work is funded by the UK Ministry of Defence. So thanks to them.
Thank you very much indeed, Rich. Are there any questions on the floor? Don't see any. Okay, well, no questions. Let's move to the next presentation. This is from Johanna Tumnoy. I hope I've got your name right. Apologies if not. This is going to be on Cesium-137 background measurement in the marine environment of the Asia-Pacific region to support emerging challenges of on-site inspection in seas. You have the floor, sir.
Oh, thank you for the introduction. I'm still waiting for my presentation to come up. All right. Good afternoon, everyone. I'm Johanna Tumnoy from the Office of Atom for Peace, Thailand. Today, I'm going to talk about the Cesium-137 background measurement in the marine environment of the Asia-Pacific region to support the emerging challenges of the on-site inspection in seas. Basically, my talk might be different from other OSI presentation, but I believe that will be really useful for the OSI activity in the future when we talk about the underwater nuclear explosion that might be taken anytime. Well, basically, as you know, that the CTBT is treated to ban all kinds of nuclear explosions, including the underground, in all kinds of environments, including the underground nuclear testing, and also the testing in other environments, including the underwater, using the 4 different mechanisms, including the International Monitoring System, IMS, which has 321 stations across the country. And the second mechanism is the consultation and the qualification. The third element is the on-site inspection, or OSI. The last one, the confidence building measures. But today I'm going to focus on the OSI elements because it's important to, the OSI activity is really important because the activity or the inspection will provide you the scientific evidence to prove whether or not the nuclear explosion had really occurred in the suspicious areas. But basically, over the, let's say, probably more than 10 years, the PTS has, invest huge amount of the time, resource, and budget to develop the OSI capability, including the development of the OSI manual, on-site inspection operation manual, to develop the techniques and equipments that can be used during the OSI inspection in case of the underground nuclear testing, and also to come up with a list of the OSI relevant radionuclides, including Cesium-134, 137, iodine-131, technetium 99M, and so on. But as I just mentioned, that the treaty is to, the main objective of the treaty is to ban all kind of nuclear explosion in all environments. And last year, I think the PTS start considering and talking about a way forward in terms of OSI activity in other environments, including in seas as well. Although there are just only 8 underwater nuclear explosion taking place in the history, starting from 1946 until 1962. Just only 2 countries in the world had conducted the underwater nuclear explosions. But who knows when the next one will be conducted? Who knows where will be the testing site for the next one? And who knows who will conduct that underwater nuclear explosion in the future? But for this one, I'm just showing you the area where the let's say, polynuclear explosion taking place since 1945. Might be difficult to see that. And the top there is the locations where 2 underwater nuclear explosions are taking place by the USSR. And down there, that's a location where 2 nuclear explosion, underwater nuclear explosion are taking place in the Pacific Ocean, and the remaining 3 explosions were conducted in this particular area by the USA. Why we are interested in the Cesium-137 and what is a major source of the Cesium-137 in seas? As I just mentioned, the Cesium-137 is very easy to explain because it is one of the OSI relevant radionuclides that can be detected, that can be used as the scientific evidence to prove whether or not the nuclear explosion has occurred. And also, it has a long half-life, and it could be detected, in the environment after the explosion. And what are the sources, the major source of Cesium-137? Definitely, the source date came from the nuclear activities in the history. Definitely from fallout from the nuclear explosion taking place in the past. And from the nuclear accident, including the one in Chernobyl, 1986, releasing a huge amount of Cesium-137 into the environment and then end up in the aquatic environment. Until 2011, there's the latest nuclear accident in the history taking place in Japan, in the Fukushima, at the Fukushima Daiichi nuclear power station, releasing a huge amount of the Cesium-137 in both atmosphere and also into the sea and ocean directly. That caused the radioactive contamination in different areas of the region. By having said that, the several countries start to implement the monitoring program, marine environmental radioactivity monitoring program in, let's say, in every corner of the world. But I just would like to focus mainly on my region, which is the Asia-Pacific region. When we talk about the marine environment, we talk about seawater, biota, and sediment. But for my talk, I'm going to focus just only for the seawater. Normally, there are two techniques to measure the cesium 137 in the seawater. The first one is the direct measurement. You just need 1 liter of seawater and gamma spectrometry to measure the cesium 137 in the seawater. This technique is suitable for the sample with the quite high concentration of cesium 137 in the seawater. The second one is let's say the precipitation technique. This technique involves some kind of chemical separation using the AMP, the ammonium molybdophosphate, or AMP, to extract the cesium 137 from the seawater. This technique is appropriate for the sample with the low concentration of cesium 137 because this technique requires more sample for the analysis along with the gamma spectrometry technique. Here is the result from the, let's say, from the previous, measurements. Basically, for the Asia Pacific region, I split them into 4 different locations. The first one is the Indian Ocean. You can see that we can have the highest concentration, let's say average highest concentration of cesium 137 in seawater in the Indian Ocean in 1984. This might be caused by the nuclear explosion that took place in the past. And until 2015, we reached an average of probably 1 millibecquerel per liter in Indian Ocean. The second part of the region is the South China and the Southeast Asia seas. And you can see very clearly the rapid increase of the cesium 137 in seawater starting from 1960 up to 1966 due to the nuclear explosion in the past. And then after that, you can see the fluctuation of the cesium 137 starting from 1972 until 2015. In 2015, we got an average of cesium 137 in seawater in this particular area at around, let's say, probably less than 1 millibecquerel per liter. And moving down to the south of the region, we are in the South Pacific Ocean. I think we got a similar trend, increasing of the cesium in seawater, followed by the decline of cesium 137 concentration in the seawater. In 2017, we got an average of cesium 137 in the seawater in this particular area at around, again, less than 1 millibecquerel per liter. Moving up a little bit to the Northwest Pacific Ocean, you can see the high concentration of cesium 137 in 1960s due to the nuclear explosion taking place in the past, followed by the decline of the cesium 137 in seawater until 2015 at the average of probably less than 1 once again. But for this particular area, it's a bit tricky because I did not add the concentration from the Fukushima nuclear accident into this slide. But I'm going to show you the result from the measurement conducted by the Japanese authority. You can see that these 3 locations, are close to the Fukushima nuclear power plants. You can see the similar trend, the rapid decline of the cesium 137 in seawater, starting from shortly after the accident, and then it has gone down to around 50 millibecquerel per liter for the station that's close to the nuclear power station. From the offshore station, you can see really clearly that the concentration is much lower compared to the stations close to the power plants. The concentration is around 1 up to 10 millibecquerel per liter from offshore stations. I'm coming down to my conclusion. In 2015, we found an average of 0.8 to 0.95 millibecquerel per liter in the Indian Ocean, and an average of the 0.13 to 0.61 millibecquerel per liter in South China and Southeast Asia. In 2017, we found an average of a range of the 0.72 up to 0.75 millibecquerel per liter in South Pacific Ocean. And in Northwest Pacific Ocean, we found a range of 0.5 to up to 3.44 millibecquerel per liter. And definitely for the Fukushima nuclear power plants, the concentration is higher than those areas that I already mentioned before. We found a range of the 1 up to 56 millibecquerel per liter in 2018. Last but not the least, I just would like to thank you, the Asia Pacific Marine Radioactivity Database and also Marine Information System, maintained and operated by the International Atomic Energy, the IAEA, for those kind of information that I already presented to you today. I think that is the end of my talk. Thank you. Thank you for your attention.
Well, thank you very much indeed. So the floor is open for any questions. Oh, I see one in back, Brian Milbrath.
Thank you for your talk. When we developed the relevant radionuclide list, we had the concern about cesium-137 because it's so ubiquitous due to its long life, which makes it useful. But so there's kind of an understanding that detection of cesium-137 by itself isn't enough, that you also need to detect and measure cesium-134 and then do figure out the ratios, and that gives you some discrimination between recent nuclear explosions and older events. So I don't know if the data that you have access to has cesium-134 measurements, or maybe also some of the other OSI relevant radionuclides. Those could be more interesting to find out if those are in quantities different than one expects on land, to see how it affects the high seas inspections. Thanks.
Right, as I just mentioned, that I got the kind of information from those two databases, and they got the cesium-134 information as well. But then we can use it, I mean, if we would like to do the ratio between 137 and 134.
Any other questions? No? Well, thank you very much. Let's move to the next presentation. The presentation that appears on your program, T2204, Environmental Radio Xenon Activity. The presenter has withdrawn from the conference, so that will not now be presented. That being the case, we'll now move directly to Laurel Sinclair from the Canadian National Data Centre. She's going to present on project on gamma imaging for on-site inspection, reconstruction of an extended source in a restricted access zone. Laurel.
Thank you. I'm Dr. Laurel Sinclair. I'm with Natural Resources Canada at the Canadian National Data Centre, and I'm going to talk to you today about gamma imaging in on-site inspection, and in particular how this technology can help in a situation where there's a zone that's restricted from entry. Do I do it. Okay, we'll skip the outline. So this is a situation that actually happened at the 2014 integrated field exercise. I wasn't there. If people were there, please correct me if I say something wrong, but my understanding is that there was quite an extensive area which was initially restricted by the inspected state party from entry. And I understand that backpack surveys and other mobile surveys were conducted around that perimeter. In particular, it was possible from an area, which I think was around here on the cliff, to look down at the features that were of interest in the restricted area that seemed like they might be emitting radioactivity, but not really possible to know without getting in there. So I think that looked like that. And I refer you back to a presentation from 2017 Science and Technology Conference, where my colleague looked with the same detector at the CTBT relevant radioisotopes and asked what the sensitivity of this detector would be from that distance. In this presentation, I'm not going to be looking at particular radioisotopes and talking about sensitivities. What I want to talk about is what would happen if we could move to several different positions around the perimeter and look in, and is there a kind of method that we can use to reconstruct the spatial distribution of the radioactivity that's coming from that area. I don't want to lose any time talking about gamma imaging because I've got exciting trial data, which I think is much more interesting for you to look at. So this is a technique that's easy to reference on your own if you'd like to. But just the high level, oh, wow, I have it right there. That's nice. The high level overview is that you need a detector that's capable of tracking a gamma ray that impinges upon it. So you need to be able to tell how many times that gamma ray scatters, and you need to be able to measure the locations and energy deposits of each individual gamma ray that interacts within your detector. If you can do that, then you know where that gamma ray came from up to an azimuthal angle, which remains uncertain. So for every good gamma ray that you detect within your detector, you've got the location of the source on a cone-shaped locus. And if you can get several gamma rays, obviously you can project, and that's also a kind of tomography, into up, down, right, left space, and see where those cones overlap to build up the image of the source. This is what our detector looks like. I guess the highlight that I really want to emphasize here, without going into all the details, is that our detector is composed of solid scintillators made with cesium iodide scintillating material, so it's very similar to the kinds of detectors that are often used in mobile survey for mapping, the aerial survey detectors, backpack detectors, etc. We get very high sensitivity with low cost so that we're able to do mapping as well as the gamma imaging. So now I'll just bring home that sort of first level of tomography that builds up the gamma image with some real data from a trial. But here I'm just showing the very first good gamma ray that was collected and reconstructed, and you can see you get one locus of possibilities for where the source could be. After a couple of seconds, you're starting to build up a sense that there's some pile up right there. Maybe that's the source, the direction toward the source. And then after a few minutes or so, you've got a very clear indication in terms of up, down, right, left of where that source is. So we take the contours of that back projection image and we co-reference that with the image of the field of view, and that gives us very strong indicator for where the source is. If there are items in the field of view, then you can use your kind of human intelligence to make an assumption that probably that it's that item, that building or what have you, that's where the radiation is emitting. In this case, we're just looking, all we can say is that there's a source in a distance, sort of near the horizon. We really don't know anything about how far away from the detector is, and there's no object in that to reference that, that image to. So we really want to try and get around to multiple angles and see if we can get a geographic location for the source rather than just that angle to it. So I'll show how that works. I think this is a fairly new methodology, so it's still kind of interesting to break it down a bit. This is simulation of a point source that's at this location, and then there's the image from one field of view looking up, down, and right to left, and we see that we can tell where the source is, and it's on the horizon, of course, because this is a source on the Earth. So we're going to take a slice with some width across the horizon and now make a top-down view. And the truth is that we don't actually have any knowledge of where that source is in terms of the distance from the detector. We just know it's somewhere along that line. This is the true location of the source. And now we go to a second viewpoint, and of course we can do a classic triangulation to get the, a geographic location now for that source, which could have some interest if you know some features or fissures or something like that, say, that might be emitting radioactivity. Now you have a geographic location for your emitter. We can throw in more locations for the gamma imager and build up more of a distribution for the source. We have a better confidence if there were maybe multiple weak sources or the source had some extent, if we can get around to the restricted zone to multiple points to view from. Right, so now it gets more interesting with real data. That was simulation data, but this is one of the trials that we conducted a couple of years ago. We're also involved in support to nuclear security. This is part of the build-up to a G7 meeting that was held in Canada in Charlevoix in 2017. And the image that you see on your right here was collected actually before the trial began. So we're just in the parking lot, we're getting ready in the morning, and on this display, which shows our gamma spectra as a function of time, we can very clearly, you can't, but we could very clearly tell that something new had appeared in the spectrum with a lot of, there's a barely visible peak here and a lot of downscatter, which is indicative of a heavily shielded source. So we choose to image that source. I hope you can see it with the brightness in this room, but we get a very clear red dot on the far side of the parking lot from where we're seated, and that's actually the source inside its pig, inside the transportation trailer. On the surface of that transportation trailer, it's okay dose rate for public occupations. This is a very weak source that we can image very clearly from that distance. Now the trial starts. We leave that parking lot, we go driving up and around the play area, and we get a couple of hits that you can very clearly see on the map of count rate versus location. But with this quality of information, you don't know. Is it two sources, one on the right of me and one on the left of me? Is it one source in the middle? So you really need that detector to give you directions as well. So we can see how that, with the direction information, it gets much more clearer that the source is in the middle of that loop. And then if you start using, of course, your human ability to interpret what you see in your environment by overlaying the back projection image on what's around the detector. And we can see that the source is probably coming from that house. We get to two more points of view from which we're looking with that imager, and the evidence gets very strong that it's coming from that house. In particular, I really like this last image where we're leaving the experimental area and the source is reconstructed. The imager is doing its best to tell you that the source is just just outside its field of view, in fact. This trial is even, I think, more. I have 3 trials to show you. That was the first one. I've got 2 more. This trial is, I think, highly applicable to the situation that would happen in an on-site inspection. It's over a very large area, and my read of the regulations for CTBTO is that quite a large area could be restricted by the inspected state party from the inspectors entering. Here's the experimental situation. We have a source which is itself over 100 meters long on one of its sides. It's a very hot source, about, what did I say there, 35 gigabecquerels of lanthanum 140, so it's, it was handled robotically and distributed over this very large area, and the imager was outside of a very large restricted access zone, following a path that I've shown here outside the red square, and it never actually comes closer than about 200 meters to that extended source. Here it is. It's sat on the top of a BV-206. This is an aside. This trial was actually set up for UAV overflight studies, and I do have a poster on the UAV measurements if you want to come by this afternoon or tomorrow. But from the perspective of the Compton imaging analysis, we kind of use the UAV overflight data as ground truth. So what we know is that the source was actually not distributed evenly over that L. It was primarily located on the long part of the L. You'll need that when you see the Compton imaging results. So here we are now from just this location here, looking out at the L, and we just see something on the horizon, not a good sense for what the shape of it is or where exactly it is with respect to the length along the line from the imager. And now I'll just cut to the chase. If we throw in, we managed, it was February in the prairie, so in the middle of the melt, very difficult operational conditions, but we managed to get 6 locations with the imager around that perimeter. And I hope you can see it with the light in here, but you can download the slides anyway from the website if that's not the case. It shows very clearly a concentration of radioactivity along that long arm of the L, where we know that the radioactivity was actually distributed. So I'm quite excited about this technique for on-site inspection, and I hope other people are too. If there are any doubters in the room, I thought I would present this as well, which is what we would have expected to see had the radioactivity been evenly distributed over a square. So this is a kind of sensitivity function for the detector's response if we consider the detector to be consisting of all of those different locations of inspection. The analysis is ongoing to learn how to unfold this response map from the product that we produce, but I think the raw product, without even unfolding for this uneven response, is still very indicative. All right, next and last field trial result is from a smaller scale dispersed source, but we had friendlier experimental conditions. We were able to collect a slightly better quality of data for this trial. So we have two sources. One of them is 3 times the strength of the other, and each one is distributed over a square that's 12 meters on a side. Here's some shots of our gamma imager crew collecting data, and you see kind of the quality of image that we would get in real time from one vantage point. It's clear that there's something out there. It's probably extended somewhere near the horizon. Not exactly sure what its extent is, though. This time I'm going to show you first the response function to not take anything away from the excitement of the actual data. So this is using simulation to say, suppose we had, the source had been extended over the whole field, what would we have seen? So obviously our response isn't completely even. In the corners there we have less sensitivity, and we'll work on correcting for that. But jumping now to the result from one vantage point, that looks like this. So we're at this vantage point right here. All the vantage points are shown by the red diamonds. So from this vantage point right here, we can already see that the distribution of radioactivity is not consistent with coming from a single location. There are apparently multiple locations, at least 2. So we perform the slice in the horizon and then back project basically this plot to show the range of locations over which the source might be, and then add in all of the rest of the other locations and make the tomograph that shows our best estimate for the locations of the sources. And we see indeed a very high probability for a source to be located within the magenta square, which is where the hot source was. We are able to discern the presence of the weaker source within the dashed square. We even see an indication within this dotted square of a pileup again, which is actually where the contaminated equipment was stored. So we can really make a 2D map of radioactivity from sitting at the perimeter of a restricted access zone. For operators who may have difficulty in the field spotting those anomalies, it's possible to make all sorts of different products, of course, to help them. This is just very simply a thresholding at 60% of the height of that probability distribution, so that it's then very clear that there's a high concentration of radioactivity and a weak concentration of radioactivity at a different place. So to conclude, this is actually more of a summary than a conclusion. You can use a Compton imager if it's made from highly sensitive material as a mobile survey spectrometer. You can do mapping just with that device, never mind the fact that it's capable of imaging and directions. Why not make your breadcrumb trail with this device that has more capabilities? From a single vantage point, you can get some information about the distribution of radioactivity in a restricted access zone, and if you can get around the restricted zone perimeter and collect multiple images, then you have the possibility to actually get georeferenced spatial distribution of the radioactivity within the restricted access zone. Thank you very much for having me, and I thank all of my collaborators.
Thank you very much indeed, Laurel. Does anyone have any questions? Yes, sir. If you could wait till the microphone comes. If you could say who you are and where you're from, please.
Hello, my name is Austin Short from the UK.
Hi.
I studied radiation physics. I was wondering if you saw any hot spots from scattering, so any dense objects nearby that might have looked like a source, but they're actually just scattering the primary radiation.
That's really fun to do. We do that sometimes. We haven't done that in this trial. So what happens there, actually, I sort of set that up by showing the first image of the truck that had the, where the source was in the pig. The way these images have been made, we have selected only total energy deposits consistent with the photo peak. So then you really get to the primary emitter. But if you move further down in the energy spectrum and you select the scatter, then yeah, you see what's shining, which is the scattering material that's between you and the source. Yeah.
Okay, any further questions? I don't see any from the floor, so I shall exercise chair's prerogative and ask one myself. In your closing image there, I can see some drones, and in one of your earlier slides, you had imagery taken from our drones. What sort of altitudes can they detect the source?
We flew that drone at 10 meters above the source. So the sensitivity, of course, is a function of altitude. Those are small drones that can lift about 3 or 4 kilograms of sensitive material. So from 10 meters or so, we can see down to background dose rates with that quantity of solid scintillator.
Okay. Thank you. Okay, no more questions? Well, thank you very much. So we are a little bit ahead of time, but I don't propose to let people sit around for 15 minutes doing nothing until the next scheduled speaker at 3:45. So let's now move to what will be the final presentation in this session. That's Andrei Belashov, UNE's subsurface signatures detected by active seismic surveys at the Semi-Palatines test site.
Okay, thank you. So, good afternoon. So, in my presentation, I will talk about the underground nuclear explosions in the vertical boreholes and about the active seismic methods in the refracted diving waves modification. So, if we're supposed to develop the on-site inspection geophysical techniques properly, so we need to use the realistic models of the underground nuclear explosion. And for that, of course, we need to have the idea about the real subsurface signatures from the real underground nuclear explosion. Because I unfortunately saw in some articles and in some presentations from different conferences, including this one, that researchers are often using very simplified models of the underground nuclear explosions, like this one, for example. So here I will show some examples of the some kind of realistic models of the single underground nuclear explosion. And the first one, we often show it, so we took it from the Adushkin and Spivak article. So this is the generalized model of the typical zones of the rock disintegration. So this model was received from the experimental data from the Semi-Palatines test site also. And here you can see that there are several different zones of rock disintegration with different configuration and different physical parameters inside them. And for example, in the upper part of the section, you can find the spalt zone and the common fracturing zone. So the next one, this is the results of our active seismic investigations at the Semi-Palatines test site. So in the top, so this is the velocity section from the refracted diving waves, and in the bottom, this is the energy field from the diffracted waves. So the vertical scales are different here. So, and here you can see that for the upper part of the section, you can definitely find the spalt zone, like here. And you can see that the configuration and the structure of the hypercentral area is really complex. So this is another one, investigations from other borehole. And for the refracted waves, here we have the sections before and after the explosion. And again, after the explosion, we can see the appearance of the spalt zone in the upper part of the section. And again, the configuration and the structure of the hypercentral area is also very, very complex. But that was the situation with a single explosion. But of course, that the potential treaty violator, he can make the forbidden nuclear test in other conditions. For example, he can use some old nuclear infrastructure with old underground nuclear explosions. So here, just for example, here the places with the dense distribution of old underground nuclear explosions. So he can use some place with more or less modern underground chemical explosions. And in this case, of course, the integrated impact of the old explosions will destroy the geological media, so the signatures from the new underground nuclear explosion also will be really different. So, of course, using of the unrealistic models will lead us to some bad results. So the purpose of my presentation, maybe as a first approach, is to define for the active seismic some target objects in the upper part of the section, data related to the underground nuclear explosions. And also I need to mention that all the results that I will show you here, they are received from the data basing on the open sources, and here's the references on them. So, so the Institute of Geophysical Research of National Nuclear Center in Kazakhstan made the active seismic investigation at the place of the borehole underground nuclear explosions. So here you can see the system of observation, 8 parallel profiles, 6 kilometer length. So the distance between the shot points was 500 meters, between the receivers was 125 meters. And as a source of the shot points, we used some small chemical explosions with the yield up to 40 kilograms. Sorry. So this is the zoom of the 2 profiles, profile 0 and profile 2. So here at least 5 underground nuclear explosions affected on the profile 0. So this situation we can regard as the situation with dense distribution of the underground nuclear explosions. And only 2 profiles, or only 2 explosions are affected on the profile 2. So this situation we can regard as the situation with single explosions. So both situations we have here. So further in my presentation, I will show the results basing on these 2 profiles. So first thing that we're receiving, this is the seismograms. So on the right figure presented the example of the seismograms for the shot point 4500 for the profile 0 and profile 2, and in the reduced time scale to have better time resolution. And the position of the underground nuclear boreholes along the profiles are given here. So, and here, even at the first stage, even at the seismograms already, we can see some typical features of the underground nuclear explosions impact on the surrounding media. So, for the situation with the dense distribution of the underground nuclear explosions along the profile, we can see the creation of the low velocity zone in the close to the shot point area. It's marked by red color here. And we don't have such zone on the profile 2 where we don't have any explosions there. And for the profile 2, in the far away from the shot point part of the seismogram, we can see the localized zone of travel times anomaly that are related to the impact of the underground nuclear explosion, single underground nuclear explosion on the profile 2. So here's the observed travel time curves from the profile 0, it marked by blue color. For the profile 2, it marked by black color. And again, here the position of the nuclear boreholes is shown here. So by blue color marked that boreholes that affected on the profile 0 only, and by the red color marked the borehole that affected on the both profiles. And here, for that interval of the profiles where we don't have the explosions on the profile 2, so we can see that the velocity of the close to the shot points part of the travel time curves on the profile 2 is higher than on the profile 0. For that area, when we have the influence of the underground nuclear explosions on both profiles, we can see that the velocities are equal. And again, for the faraway parts of the travel time curves from the profile 2, we can see the anomaly of travel times that is related to the influence of the single explosion on the profile 2. So this is a good methodical result because we can use these like some searching criteria. Here, this is the velocity section. So we build them using ray tracing method and SACE-wide software. First, about the depth of the explosion. So why I'm always talking about the upper part of the section. So at the left figure, you can see the seismic rays diagram and the position of the hypocenters of the explosions. And you can see that the density of the rays is not enough to receive the comprehensive information about the velocity parameters on the depth of the hypocenters. So we artificially limited the sections to the depth by 300 meters. And here again, on the sections, we can see that in the situation with single explosions, in the epicentral part of the explosions, in the shallow depths, from 50 maximum to 100 meters, we can see appearance of the zones, localized zones of low velocity. So these are the SPAL zones, which I talked earlier. And in the situation with dense distribution of the explosions, these localized SPAL zones, they are transforming into the continuous SPAL layer. And under the SPAL layer and SPAL zone, this is the layer of common fracturing. So in the bottom, this is the models of calculated elastic parameters, such as Poisson ratio and VP to Vs coefficient. And so inside, within the SPAL layer and SPAL zone, these parameters characterized by anomaly high values. And for the common fractional layer, it's characterized by increased values, but not everywhere. So here we can define two main target objects in the upper part of the section. So this is the SPAL zones and zones of common fracturing. Then we compared before and after explosion parameters. So before explosion parameters we took from the core samples from the nuclear boreholes. And at the figure it's marked by black lines, black color. So the green dashed line, this is the SPAL zone. The blue dashed line frames the zone of common fracturing. And so here for the velocities. So the velocities after the explosion are less than the velocities before the explosion for both zones, for SPAL zone and for the zone of common fracturing. For the Poisson ratio, so within the SPAL zone, the post-explosive Poisson ratio is higher than before explosive. For the common fracturing zone, they're most equal, but here you can see that the Poisson ratio before the explosion here also pretty high. This is the borehole 1321, so these are some kind of local geological conditions. And on the right figure, this is the comparison of the Poisson ratio before and after the explosion. And for all the boreholes, after the explosion, the Poisson ratio increased. And this situation is typical for the fractured and fluid-saturated rocks. Then we calculated such parameter as crack density. So this is the relation of the volume of all the cracks to the representative volume of the rock. So we use the relations for the elastic parameters, such as bulk and shear modulus, and other parameters. So this is our searching parameter. And after some simple recalculation, we received the relation for the crack density. So we calculated it, and for our boreholes, it changed from 0.02 to 0.45. And I can say that the crack density mostly depends from the technical parameters of the explosion. First of all, from the yield, and slightly depends from the geological conditions. First of all, from the position of the faults. And here's the last diagram. So as I just told, the crack density depends from the technical parameters of the explosion. So this is the relation, and this relation could be useful in the situation when we will not have the information about the technical parameters of the explosion, the depth and the yield. So we can take it from this relation more or less precisely, of course. And the last, this is some little short example of modeling, because as we made the critics to the researchers that are using the simplified model, so of course we will need to try our own modeling using more or less realistic model. So of course this model is also pretty simplified because we didn't input here some geological details, and first of all the position of the faults, but the faults are very important from the point of view of configuration of the zones of disintegration. But this is some kind of generalized model for the semi-Platin's test site. And here are the results of modeling, again, very briefly. So what we can see here in the wave field, again, for the travel time curve that are situated in the vicinity of the underground nuclear explosion, we can see the creation of the low velocity areas of refracted waves that are related to the SPAL zone, and we can see a lot of reflections that are related to the hypercentral area. For that travel time curves that are situated outside the underground nuclear explosion, so we can see the increase of the travel times above the SPAL zone, and the hypercentral area is characterized by interrupting of the observations and creating lots of outrunning pickings. So the wave field, even if we use a simplified model, is really complex also. And a couple of words in the conclusion. So I showed here just two potential situations for the on-site inspection. So the situation with the single underground nuclear explosion, that is better for the on-site inspection, of course, because the target objects are more contrasted, it's more easy to find them in the subsurface. And situation with the group with the dense distribution of old explosions. So for the on-site inspection, of course, it's more difficult. But of course, during the real on-site inspection, the number of situations can be endless. So my recommendations, of course, they're very, very obvious, but sometimes it's necessary to pronounce some obvious things. So first, of course, this is necessary to collect as much as possible existing information about the results of active seismic investigations at the places of real underground nuclear explosions. And the second, so the theory without practice is nothing. So it's necessary to make some natural experiments, again, at the places of real underground nuclear explosions, not at some kind of geological limitations, natural cavities, because that is different. So at the places of real underground nuclear explosions. So thank you.
Well, thank you very much indeed. Floor is open for any questions. No, I don't see anyone rushing to grab the microphone. Well, thank you very much. Just before we break a few minutes early for the coffee break at 4 o'clock, it seems to me, having listened to the presentations, that there are some very promising technologies and techniques that have been developed further that are going to help with some of the challenges that we face in on-site inspection. Measurement restrictions, to name but one, access to restricted access sites through remote sensing. Again, very important, rapid ways of determining, characterizing in situ rocks, which will help with OSI, and further modelling work that's been done on active seismics, which has been a relatively neglected area over the years in OSI. So thank you very much indeed to the presenters. I hope you found that informative and useful. We will continue here after the coffee break at 4:30 sharp. So hopefully I will see you all back here again at 4:30. So make the most of the extra few minutes you have for the break. Thank you. It's not practical because you can't just wait here for 10 minutes. Yeah. Good afternoon, Vitaly. Hi, Craig. Yeah. I was just a colleague of mine. Yeah. So, tomorrow, yes. Yeah. Yes. Yeah. Yeah, hopefully we've only got 2 presentations next time. One of them, hopefully, I mean, we haven't turned up with their slides yet, so I was hoping to go, because that's quite an interesting one too. Yeah. Oh, tomorrow. We'll do that tomorrow. Yeah. Yes. We'll have to keep going for an hour and a half. See you, Vitaly. Afternoon, Craig. Dealing with OSI. So Craig will sit at the desk when I'm sitting up. He was there at the last session. So his job is to Okay. 8 and 15, yeah. Okay.
It seems we only have two.
Yes,
Three?
two, I've just seen them.
Two.
But then we still have to do these other ones, the 2 point,
Yeah, we have three.
T2, 3 as well. He's
We
got-
will do?
Yeah,
No.
yeah.
Why we do?
Well, because we're on the podium. Yeah. He's going to give me a list
Really?
of yeah.
They told
I
you?
asked him, yeah.
Okay.
'Cause I said, who's chairing this then? He says, well,
Where is the chair for this two?
I don't know who's doing 2, 3.
So that means we will first do the 2
We'll do the
hour
yeah,
session and then we'll do that
yeah,
session?
yeah.
Okay.
Hopefully not 29 of them, because if it's a minute each, that's half an hour. Well, we will take, I mean, that'll be 17:17.
But the thing is, after we will move to the posters need
Yes.
need leave the room. I don't know why.
Yeah.
Which the audience will be the same
Yeah, well,
because they after this
Yeah.
preview
Yeah.
session they will move to
Yeah.
there.
yeah. Okay, we're going to start. Okay, everybody, I think we should get underway again. It's 4:30. We have on the program 3 presentations in this session, plus a very short 1-minute presentation on the posters for OSI T2. There'll also be a presentation on posters for T2-3 as well at the very end. So the first presenter in this session is Gustavo Gerard from the OSI division in the PTS. Gustavo is going to present to us how to develop a credible scenario for large field exercises, scenario task force activities. Gustavo.
Thank you. Thank you, John and Honmei. Good afternoon, ladies and gentlemen. In this presentation, I will try to share with you the activities of the scenario task force, aimed to develop a credible scenario to be used in the large field exercises that we are preparing for next year. So the OSI exercise plan that was for 2016-2020 was approved by the PrepCom in 2016. And this exercise plan supports one of the 2 strategic goals of the PTS medium-term strategy at that time, namely the development of OSI operational capabilities. In that context, exercises are seen as crucial element to test progress in implementing what we call the OSI action plan for 2016-2019, and evaluate the action plan contribution to the further build-up of OSI operational capabilities. The OSI action plan is an ambitious undertaking which includes tabletop exercises, field test, direct exercises, and a series of build-up exercises that will cover all the phases of an on-site inspection. In the beginning of 2018, the PTS, with the support of state signatories, developed a concept for the next series of build-up exercises. The objectives of the build-up exercises were stated and are, in a few words, to test progress that has been made as a result of the implementation of the OSI action plan and its contribution to the OSI operational capability, to validate key deliverables of OSI action plan projects, to validate the program of the 3rd training cycle for surrogate inspectors, to test revisions and areas in the draft OSI operational manual in the model text that were not previously exercised, to ensure that areas of existing operational capability have been maintained, and of course, identify areas for further improvement. To achieve the expected outputs, that meaning from the exercises, meaning to gain a comprehensive set of exercise lessons as a basis for future OSI development, to benchmark the progress made toward further developing of the OSI regime since IFE 14, to provide feedback to the draft of OSI operational manual model text, and to validate the third training cycle. All this within what we call the real zero growth budget, the approach of the conduct of an exercise, integrating the third training cycle, concluding field exercise, will cover all the phases of an inspection, and it was decided to split it into 3 separate build-up exercises. The first one will cover the launch phase, what is known as the launch phase of an OSI, which it starts at the moment an OSI request is made until the deploy of an inspection team to departure from Vienna. This exercise will be conducted here as a command post, here in Vienna as a command post, in the headquarters, mainly in the VIC and at the test center, and it will happen in November this year. Subsequently, a second part will be, of these build-up exercises, will be a field exercise, and this exercise will cover the initial period of an inspection, that this lasts within the 25 days from the OSI request submission approval. The exercise will be conducted in June in Slovakia, and it will start with the point of entry activities, and it will end through the submission of the progress inspection report. During this exercise, initial inspection activities will be implemented, and those techniques as stated in Article 69 of the protocol will be applied. In the last field exercise that will be conducted in September 2020, Article 69 continuation period techniques will be implemented, and post-inspection activities will be conducted. The exercise, the build-up exercise is a PTS project that comprises the following stages. There is, at the beginning, there was a concept development. Then we enter into the planning, preparations. Then we will go into implementation of the exercises and post-exercise follow-up. The development of the exercise scenario spanned through the planning and preparation stages of the build-up exercise project. A scenario task force was established with the purpose to develop a contiguous scenario for the 3 build-up exercises. The scenario shall be technically realistic, rationally coherent, temporally logical, and intellectually motivating, so that all or the majority of OSI processes, procedures, and techniques can be adequately tested. During the concept development, few assumptions related to future large exercises, financial resources, state signatory support were made. Significant OSI relevant development include the use of the new ESMF at the test center, the new OSI Operation Support Center located at the CTBTO Operations Center in the VIC, and the use of the recently developed Geospatial Information Management System for on-site inspections. You can find further information on these 3 main infrastructures, one by visiting the test center during this SnT conference, visiting the poster hall with a poster on the Operation Support Center and the CTBTO Operation Center, and some demonstrations that we are running on the GMO system during the coffee break. This will be tomorrow in the afternoon. So the criteria for the scenario shall include scientific credibility, implementability, consistency, coherence, and last one being realistic by taking into account real geographic features. To cover adequately all technical and non-technical scenario elements to be developed in a comprehensive and coordinated way, the STF, the Scenario Task Force compositions, include 13 state signatories experts, which were selected based on their experience and expertise on the different OSI techniques, host country representatives, and 3 PTS experts from OSI and IDC divisions, all of them supported by the PTS. The STF structure includes 6 sub-teams, one of them focusing on the development of the full storyline of the exercises, 4 other sub-teams concentrating on BOV MSIR, radionuclide and noble gas measurements, seismic geophysical techniques, and non-seismic geophysical techniques. And the last sub-team was developing the ISP strategy for the exercises. The scenario should simulate the realistic planning and conduct of an OSI by the inspection team using all available inspection techniques in an integrated manner. To that end, the STF implemented lessons learned from IFE 14 and high-level scenario considerations. The scenario is being developed in 3 levels. The first level is a credible storyline along the inspection. The second one is, in this first level, also a triggering event was developed, and the ISP country profile and strategy was also developed. Then we move into a subsequent second level. In this second level, scientifically consistent set of observables were proposed, and the definition of the data flow through the exercise was also proposed. In that respect, we need to understand that the data flow will slightly change between the launch phase of the exercise and the field part of the exercise. And finally, in the third level is to develop data injects, taking into account the played roles that we expect to be played during the exercises, even as a requesting state party observer, the inspected state party, and so on. The method of work of the STF included systematic work in STF meetings, experience and expertise of the STF members, open-minded and open discussions were conducted and are being conducted. And we selected what we call the what-if approach, that for each expected activity, different alternatives of the outcome expected from the inspection team are analyzed, and the scenario is consequently developing in that way. We have at least one visit to the expected site to conduct the field activities, and this was for familiarization, site selection, site characterization and surveys, and to conduct site monitoring visits. The STF main deliverables includes the type of the triggering event and its parameters, the storyline scenario, the package of documents of launching an OSI, meaning the IMS data, the request, the executive council decision, and so on, guidance on the ISP strategy and possible non-technical injects, location of the event and other areas of interest in the area where the exercise will be conducted, a set of observables that will be included in the game, and the approach and practical guidance for their simulation, full and sanitized scenarios, exercise implementation timetable, and so on. For those that were involved in IFE 14, because as you may understand, I cannot provide any substantial information on the scenario that we are developing, because we expect that some of the people in this audience will play in that exercise. So, but for those that were involved in IFE 14, this is a good example with pictures and a map how it was developed during IFE 14, developing some preparations for the exercise, and now the inspection team need to decide what are those observables they are seeing. One of the first things that we decided during the development of the concept of the exercises was to request for peer review of the scenario. Because of the nature of the build-up exercise being split into three, we decided to have two scenario peer reviews. One was already conducted in March this year, and that peer review covers mainly the storyline and the products prepared for the launch phase exercise. The peer review team is composed by 5 state signatories experts with the relevant technical and OSI experience. The objective of the peer review is to independently review that the exercise scenario and related products and injects are technically realistic, scientifically credible, and they support the accomplishment of exercise objectives. The SPR focus on those topics, and it is expected from the peer review team to provide to the scenario development team their recommendations in due time. So to finalize my presentation, and I believe you understand that I cannot share with you more scientific or technical information, I want to thank to all those that are part of the scenario task force, and they are supporting us on the development of these exercises. Thank you.
Thank you very much indeed, Gustavo. Floor is open for questions. Don't be shy. Come on. I know it's late.
I'm not sure I can answer, but
no, I don't see any questions. I shall forbear from asking any questions because I was on the external evaluation of the peer review process, so I know the answers. Okay, we'll move to the next presentation. It's Gerardo Suarez. He's going to talk about the potential use of interferometric techniques in the location and size estimation of suspected test sites. He's from the Instituto de Geofísica from Mexico City and formerly of this parish, for those of you who remember him as director. So welcome back.
Well, thank you very much, John, and thank you all of you for being here. And also to finish with the thank you notes, I would like to acknowledge the PTS staff and the Executive Secretary for this very generous invitation to come and perhaps stir the pot a little bit. I should say that I was talking to John and I told him that I asked for a poster presentation because it's more of a thought experiment than anything else. And they gave me an oral presentation which represents more of a responsibility that I hope I can make up. As I mentioned, it started as a thought experiment of a preoccupation that I've had ever since I was here. You know, you launch an on-site inspection. We just heard the detailed steps that will take place in the next experiment. But the team has a tremendous challenge. It has the challenge to cover 1,000 square kilometers. It's not easy for any of you who have worked in the field doing geophysical or geological work. It is not easy to cover that amount of terrain in 60 days, particularly under the pressure in which you're going to be in a real on-site inspection. But also, I think I turned it into an idea of how the PTS and the treaty in general can take on modern techniques and modern instrumentation that was not available at the time of signature. And for that, I chose interferometric techniques. And the reason I chose it is, first of all, because I've been working with a group of students on using these interferometric techniques on a variety of topics: earthquakes, landslides, subsidence of basins due to water extraction, civil works, and so on and so forth. And the second one is that, as I will show, it was a very heavily guarded military secret. Interferometry has been known for many, many years. Countries, particularly the P5 in general, have been conducting interferometric analysis using satellite-based radars for many, many years. But all of a sudden, this technology became public, and now you can access open source data from the European Space Agency that is essentially free, of very, very high quality, as I hope I will be able to demonstrate. And what better way to test it than to use the latest and largest nuclear test of the DPRK on 3 September 2017. So let me I do not ignore, I should say, I was not going to say, but I should say that having worked here for several years, I do not ignore the diplomatic and political challenges of proposing to use new technologies. But I think, at least at this level, in a science and technology conference, it should be something that has to be discussed, because these are technologies that are available to the OSI, to the PTS, and to the CTBT in general, and I believe they should be considered. Let me give you a little bit of the background. Pabian and Koblenz and Wang and his colleagues, they both last year published papers, and that's where the idea came up to me, using precisely these interferometric techniques of satellite-based instruments to map the deformation of the 3 September 2017 nuclear explosion in Mount Mantap. And the results were very, very interesting. And this led me to say perhaps we can do it in a slightly different way, using a broader area, and see exactly what happened, and see if this technique could be used in the future. This is the result of Pabian and Koblenz, which is an extraordinary paper. I would really recommend it. And what they mapped it in a slightly different way as these results are usually mapped. They mapped, you can see the red zone corresponds to a deformation of about 0.4 to 0.5 meters, presumably coinciding with the test, and let me get to that. And then the rest, in the lower part of Mount Mantap, you know, this green, which represent areas of deformation with slightly less than 10, 15 centimeters, they don't use vertical deformation, they use what they call true horizontal deformation, but that's already in the noise range. So we said to ourselves, okay, they use for that these TerraSAR images. Okay, they use the TerraSAR images that they mention in the text. Well, what if we use the TerraSAR data is open, but you have to pay for it. It's costly if you want to go to the very low resolution that they use. So what if we use open source data like the one provided by the Sentinel mission of the European Space Agency? It's open source. You can download all the scenes that you want, and it has two extraordinary advantages. One, the revisit times of the satellites, and what I mean by revisit sites is how often the satellite comes over the same region has come down to about 6 days. And secondly, the delivery of product is extremely rapid, and I think this is a reflection of the improvement in data collection and storage that we have witnessed in these past few years. So the purpose, again, is can we, for example, use open source data? And that is a big advantage, I believe, that it is open source, not because it costs money, perhaps the PTS could afford it, but it's readily available to anyone who wants to reproduce the results. How will these results compare with a much more expensive and relatively restricted data from other satellites? Perhaps some of the best are the TerraSAR X or the ALOS satellites of the Japanese constellations. And second, and finally, could INSAR and other interferometric techniques be used in the different stages of an OSI inspection to guide the inspectors? It's not for attribution, but it's to guide the inspectors in their tasks. First of all, let me start with this business of the difference between high-resolution images for TerraSAR X and images from Sentinel-1. And this is an image of the Mexico City airport, which we, for several reasons, are working on. It's a very hot topic in Mexico City these days because there is quite a bit of differential sinking in Mexico, and in particularly northeastern Mexico, where the airport and the supposed airport that was going to be built are located. So it's important to know. And that is the airport. You can see the black top is the airport. If you look close enough, you can see here the white, these white buildings are Terminal 1, Terminal 2, but you really cannot make out too much. You have to do quite a bit of processing, which we do. If I compare that to the TerraSAR X images, well, the image becomes a lot clearer. You may say it's still blurry. Yeah, but it's much more clear. The black top that we saw here becomes very clear that there's the runaways, some of the service taxing runaways. The buildings of Terminal 1 become much more clear, so do the buildings of Terminal 2. And why is the reason for that? Well, the reason is you get what you pay for. And in the Sentinel-1 mission, which is an extraordinary piece of data, I must say, and the one we normally use, well, they use C-band, and C-band means that the wavelength of the radar signals that are sent are about 5 to 6 centimeters long. And the resolution of the pixels, and you can see it here, is about 13 meters. So the lower you can come is about 13 meters without post-processing. In the case of the TerraSAR, you work on the X-band, which has about half the wavelength, so it's much more sensitive. And you can bring down then the pixel size to about 3 meters. I hope I don't offend anyone, and there are probably people in the room who know more about interferometry than I do, but this is what I use in class. And it's essentially the same, what you do is essentially the same as to what some children do, or some of us do, with a Sunday newspaper. You're presented with two images. Okay, this was flown before the nuclear test, and this was flown after the nuclear test. If these were satellite images, you would say, what are the differences? What happened before and after? Was there subsidence? Was there slumping? What are the differences? Well, the difference here, we see there are 10 differences, or I only looked at 2, but there's this a sad little turtle, it becomes a little bit happier and so on. But you do the same. You take 2 successive images. One you fly before the test is conducted, and you fly the second one a few days afterwards. And the differences you map in phase. You see, you're not going to see images like this. You map in phase. These are changes in the phase of the waves traveling to the Earth and back to the satellite. And these phases, of course, because of the wavelength and the speed of light, represent distances which, after processing, you convert. So what do we get? Well, we're lucky that the ISC and NORSAR and some of the other agencies have gotten to be so precise in terms of the location. And here, for example, you see the location of the 2003, the first nuclear test, 2006, the first nuclear test, and the size of the uncertainty that the ISC published is very large, and it's due to 2 things. Now they're using better Earth models, and secondly, there's better coverage, and they know the region much better. And if you come to a 2017 test, it is this red area. So you could say, well, inspectors will be given with a reasonable area to explore, but it's very mountainous terrain, very difficult terrain, and the inspection area will be about 3 times the size of this ellipse. So it's still a considerable amount of terrain that you would have to cover. So we conducted an INSAR, an interferometry exercise on that region. We took a slightly larger scene than the previous authors that I mentioned, and we immediately see this is the red numbers are subsidence, and presumably this is uplifting. And what we see is that there are 2 what in geology would be very typically called crowns of slumping. You know, when a mountain slumps, you see on the mountainside there is like a crescent-shaped feature, and we see very clearly let me first put it on the topography. Okay, this topography of Mount Mantap, I placed here, and I called it the IEC location, which is more or less the IEC location, but it's where most of the agencies place the epicenter. At the very top of Mount Mantap, the tunnel portal is here, which makes sense, because you have about 800 meters of overburden between the top of the mountain and presumably where the test took place, if the tunnel is more or less level, which it probably is not for water flow issues, but it must be relatively level, so it's about 800 meters. And the first thing you see is, yes, there is this crescent shape slumping with a maximum deformation of about 40 centimeters, but there's a second one right here. There's a secondary one. We have no way of telling on a temporal basis which one occurred before, which one occurred afterwards, because this is based on two images, one taken on 29 August, before the explosion, and another one taken on 5th September. But there's also, and we worked a lot on this, there's also, you see some other red areas that we could interpret also as slumping, but frankly, we did not become confident enough to say that they were. But these are very, very clear. And Young and others in the previous paper, they very clearly identify them. And there was a previous paper presented on Monday that also showed it. So what conclusions can we draw? Well, we can draw the first conclusion that radar images from Sentinel, even though they're not as sophisticated as some others that are more costly and more restricted in use, can accurately map the slumping. There is evidence of at least two main slumping crescents, and that also may explain some of the aftershocks that we saw. This is speculative, of course. We prove that, yes, with open source data, which may be more attractive from a political point of view, you could use this in the initial phase of the OSI exercise. That is, in the launch phase of the exercise. What we just heard, it would be the BUE in. I mean, where am I going to go? This gives you a guide as to where potentially you see the largest information. It was the biggest. You may not see the test. And finally, traditional test area for North Korea has shown to be highly fractured during this test, which leads to some speculation, and it's speculative and it's in red. Perhaps Mount Mantap has been highly fractured and faulted. You saw the amount of slumping, and maybe it's always in last place. Didn't do their technology improvement. And Mercedes did. And what these guys have done, for example, this is in Monaco. This is one on what you can do with interferometry, and the second one is how these could be applied as new technologies to on-site inspections. Thank you very much.
Thank you. Thank you. Do we have any questions? Yes, we have one down here. If you could say who you are, please, and where you're from.
Yeah, thank you. I am Talayela from Addis Ababa University, Ethiopia. What is the dependence on magnitude? For instance, the radar interferometry for earthquakes is much dependent on earthquake size, but mostly the test sizes are smaller in magnitude, so how dependent on the magnitude of the explosion? And I didn't see also fringes. Do you have fringes developed from the interferogram? Fringes?
Fringes?
Yeah.
Ah, okay. Well, yeah, certainly it depends on the size of the explosion. As I said, this was pretty large. We've heard numbers as large as 150 kilotons. So you expect large deformation from those. Smaller explosions will probably create smaller deformation. We see that in earthquakes. This is a technology that is now frequently used on earthquakes near the surface to understand how they deformed the surface of the Earth. And the larger the earthquake, the much better the signal you get. So we may not see a signal for a small nuclear test. And I didn't show you the fringes because I wanted to just show you the results, and I barely made it because John was waving at me. So, but yes, of course, you get fringes of different phases And you convert those through processing into true vertical changes or true horizontal changes, whatever you're looking for.
Okay, thank you. Any more questions? No. Oh, Vitaly.
Thank you, John.
If you could just say who you are.
Yeah.
I know who you are.
My name is Vitaly Shukin, former OSI task leader, working group B. Gerardo, very interesting presentation. Thank you very much for sharing this, your latest achievements. There are two aspects here. This novel technology, the technology for a site, development of tools for gathering information, but another side is interpretation. Specifically, the images which were shown by you, there are not just red or yellow, but also blue areas. What could be your explanation for this blue?
Yes, I was sure somebody would ask me. There's another aspect we were discussing coming back from lunch with Vitaly, that I'm not in any way proposing that the technology such as this would be used for attribution or to verify or to confirm that a nuclear test took place. It's simply to guide the on-site inspection to the site where we believe it is most probable that it took place. The blue has puzzled us a lot, and I just bought the Rittersaal images to understand a little bit better. I mean, this is what we had available, but I don't know. But we concentrated the processing near Mount Tap. That I must say. So that may be noise, but it's very high noise. It's also about 30 centimeters. So we just bought the Rittersaal images, similar to those other colleagues, but we're doing a slightly different processing and taking a larger view. And I can probably tell you a little bit more in a few months.
So perhaps we could wait for the next technology.
Well, it could. I hope it's sooner, but yes.
I think the key point really here is that it's a lot of these techniques we're using in an integrated fashion. No one thing is going to give us the answer, maybe one or two, but it's the totality that helps inspectors. So thank you very much. Let's move now to the final presentation in this session. So Mr. Wu, who's going to talk on utilization of unmanned system for environmental sampling in CTBT OSI. He's from the Shaanxi Thor Intelligent Equipment Company from China.
Good afternoon, ladies and gentlemen. My name is Wu Dengke, coming from Shaanxi Thor Intelligent Equipment Company, China. The title of my presentation is Utilization of Unmanned System for Environmental Sampling in CTBT OSI. First, I will begin my presentation by some retrospect in CTBT. Since the first nuclear explosion in 1945, over 2,000 nuclear tests and devices have been fired. Here's a map from the CTBTO website that shows the nuclear test sites in history. Human world has never been in such a situation. Under this circumstance, the international monitoring system was proposed. Here's another map from the CTBTO website again, and that shows all the current stations of IMS networks. According to the space that a nuclear explosion could happen in, the nuclear explosion could be divided into 4 types: atmospheric, underground, exo-atmospheric, and underwater. The IMS also consists of 4 kinds of signals: seismic, hydroacoustic, infrasound, and radionuclide. By the way, I think the model demonstration of the IMS system is just in the next room in the back. I believe you have already seen. Once a nuclear event was detected by the IMS system, an OSI might be triggered. During the process of OSI, environmental sampling could be used to collect samples of solids, liquids, and gases from above, at and below the surface to detect anomalies which could be indicator to the inspection team to extend its inspection activities. Challenges could appear in this procedure. Harsh environments like remote or mountainous area, high vegetation land, tough conditions like extreme hot or cold, wet or dry, possible high or even lethal radioactivity, and unreachable area. These all makes the challenges for OSI, especially the high radioactivity. Because of some unique purposes and specificities of nuclear test explosions, for the underground scenario, the device could be detonated most probably in a stemmed vertical shaft or horizontal tunnel. If the containment is not perfect, radioactive substances will be leaking or even venting out directly over the ground zero or along fractures to the ground. As a result, one or more contaminant areas with high or lethal radioactivity will be formed. These areas were deemed as dangerous and dirty areas where inspectors would take the highest risk of exposure if they stay or work there, especially take samplings around. Here is another a radiation dose chart from Wikipedia. The small number of sieverts absorbed in a shorter time will generally cause more damage, but cumulative long-term dose plays a big role in things like cancer risk. Another challenge of OSI is the limited personnel. During an OSI, an inspection area of up to 1,000 square kilometers will be searched by a team of inspectors with a limited number of up to 40. So what could be done to deal with the challenges? I think utilizing unmanned system in the process of environmental sampling could be a possible answer. You may ask, why unmanned system? As a development of cognitive science, artificial intelligence, etc., unmanned systems such as unmanned ground system are deemed as common test beds for testing and verifying vision, sense, cognition, and intelligence technology. As technology continues to mature and evolve, unmanned systems have been widely used in many areas. They play a very important role in applications such as nuclear leaking detection and other extreme environmental applications. The most significant advantage of an unmanned system is working in an area with tough and extreme conditions where it's unreachable by human. A highly likely scenario occurring during an OSI, as described above, is the right place for an unmanned system to come into play. Let's take a look at all the qualities that an unmanned system have. Platform. To accomplish different missions in different species, unmanned system could be in different forms, including unmanned ground system, unmanned air system, and unmanned submarine system. Mobility is a basic quality. Is a basic quality for the environmental sampling procedure. A stationary unmanned system is not adequate to complete all the environmental sampling work, especially in a large area. Control. That's the core of the system. That's the core of the system. It's a key that brings all the opponents of the system together and makes the system work properly. Performance is also an important aspect for an unmanned system to work in practical environment, not just in laboratory environment. And the last, functionality. That's the final but also the basic quality for an unmanned OSI system to finish assigned missions like gamma detection, sampling air, soil, and water. Based on all the aspects above, we can summarize 10 elements that an OSI unmanned system must have. For example, RN detector for radionuclide detection, sampling gears for environmental sampling, navigation for how the unmanned system could be navigated, like manually, target guided, or route guided. Other factors including control mode, mobility, communication, maintainability, reliability, and persistence. These factors will be discussed in the next part shortly later. Besides, the balance of size, weight, and power of the whole system must also be considered. From these 10 elements we have summarized above, here's a brief introduction of the system. Modular design to make the system easy to maintain and repair and adjust to various applications. The control mode could be wire or wirelessly controlled according to the environmental radioactivity or signal interference. Day and night duty means the sensors and control unit of the whole system should be designed with wide dynamic range, multi-terrain. As we have discussed, that an OSI could be conducted in different terrains, versatile interfaces to make the whole system easy and simple to switch to different sampling gears. Here are some technical specifications of the system. Replaceable wheels or tracks to adapt to multi-terrains. 3 navigation models, manual, target waypoints, and road guided. Reliability, the system should have the ability to, of anti-nuclear radiation, water and dust proof, endurance working under wide dynamic range of high and low temperature. The persistence of the system should be at least 6 hours, and the maximum speed of the system so far shouldn't be over 30 kilometers per hour for real applications and security concerns now. And of course, this number could be changed if the techniques are more mature and the need for higher speed is required. But now, 30 kilometers per hour is adequate. Here's a picture of a 4-wheel unmanned cart we have developed to testify the movement algorithms and related abilities. We call it Demo 1. We used a PS2 joystick to control the cart with wire. The whole system weighs 10 kilograms. This was done in January 2019. Here's another demo. Here's another picture of the tracked unmanned cart. We call it Demo 2. This one weighs 20 kilograms and movement ability is better than Demo 1 due to the tracks. It has the ability to spin, turn, climb up and down, and move directly at a maximum speed up to 20 kilometers per hour. We used an upgraded controller with a 6-inch screen to monitor the GPS and video information, and the software interface is also preserved for exhibiting environmental sensors data. Of course, it's wireless. Demo 2 card was finished in April 2019. Now, here's a piece of video clip to demonstrate Demo 2. I'm not sure how to play this. Oh, crap. Yep. Oh, I'm sorry, due to some reasons, the videos can you help me play the video? Here's a video in the presentation. Here's a video in this presentation. Can you help me? No. Oh, okay. You click on the picture. Oh.
I've never yet been at an SnT conference anywhere where there's not some audiovisual technical problem.
thank you. Yeah, that's a video clip. That's so far we have reached. Is unmanned ground vehicle the best answer? We don't know it yet, but there is some concerns of utilizing unmanned ground vehicles, for instance, the CDBT treaty and regulations, and of course, the inspected parties' acceptance. For further development, the relative technical development shall be improved to fulfill the environmental sampling work and the CDBT SOP. It is the standard operating procedures shall also be taken into consideration before we are ready to utilizing the unmanned system in OSI. Here's a concept illustration with combining robotic arms and demo tools UGV platform to fulfill the environmental sampling, like collecting soil samples or water samples. We are planning to accomplish the combination work by the end of 2019, hopefully. So in conclusion, UGV may not be a perfect way to realize CDBT OSI currently, but it provides a possible and practicable way to assist in CDBT OSI. So the works in my presentation are all done in the laboratory of Shanxi Thor Intelligent Equipment Company, which is a company focusing on developing intelligent equipment such as UGV and UAV, and hoping to end nuclear explosion. Yeah. And I also want to dedicate my special thanks to Mr. Fei Hongkwang from CDBTO, who has given a lot of advices and helps in this program. Thank you. 谢谢. Vielen Dank.
Thank you very much indeed. Do we have any questions? No, well, I've got one question. Since there's none from the floor. Have you thought about ease of decontamination of the mobile systems? Because at the end of the day, after an inspection, you may have to clean the object before you take it back. So have you thought about things like chemical hardening or making sure the surfaces are easily decontaminated?
Yeah, so far we are still building the platform, so but that's a good suggestion, I guess. I will take that into consideration.
Thank you. I see no more questions from the floor, so thank you very much indeed. Now we move to the poster introductions. We have two for OSI. We have poster 8, P8 and P15, and the usual drill is that the presenters come and have 1 minute to present their poster with no questions. So could the owner of P8 come forward, please? Hello. Hello, I'm 15. You're 15? Is the owner of poster 8 here? 2.2, yeah? Okay. Yes, P8.
Good evening, everybody. My poster title is Studying the Suspected Sites of Nuclear Test by Using Microtremor Methods. Microtremor are continuous recording with different small amplitude ranged between 0.1 to 1 micron. Its origin related to natural and artificial disturbances such as wind or human activities, factories, and so on. We record the microtremor by using recorder and short period seismometer to detect 3 components, 2 horizontal and 1 vertical. Dividing H over V, horizontal over vertical, we can obtain the dominant frequency, and we can draw contouring map to detect the frequencies. Whereas the low frequency, that's mean there is some destruction in the area. So it is refer to the location of the explosions, test explosions, and by help the other geophysical methods like seismic or resistivity, we can detect the location exactly. Thank you for your listening.
Yes. Hello, my name is Nadezhda. I'm representative of All Russia Research Institute of Automatics, Russia, Moscow. Here, we would like to present several themes of our poster. The first one is we're developing OSI training simulator 3D module for surrogate inspectors. The second one, we study and improve detection and location processes at regional distances on the example of DPRK. And the third main team is a Russian noble gas monitoring equipment called MIX. And also there are several themes, but it's the major activities. So come and see. Thank you.
Thank you very much. We have no more posters for presentations, so obviously you've heard the summaries, so I encourage you to go and see the posters and display and talk to the authors. So this concludes this session. Teacher, I hope you found it useful. So session is now closed. Managed to get that done in good time. Okay, as an announcement, the poster presentations for session T23 will take place in this room. So if you want to hear the posters for session T23, they will be starting now. Okay. Not so bad. See, nobody told us. We thought they'd messed up the program.
Yes, they should come. This is not from us.
Because we wondered, we took 29 posters.
Yeah, that's but ours is a little bit.
Yes. Yeah. Good luck.
So ladies first, and introduce you. Maybe it's good to ask excuse also because the session was closed before, but
yeah.
Yeah.
1 minute.
So we start. Yeah.
Just speak. Good afternoon. Hello. Welcome to the poster preview session. This is the first session on topic T2.3, seismoacoustic sources in theory and practice. And we have two announcements to make. One is that you are requested to be at your poster tomorrow between 2:30 and 4 p.m. I hope you got this message via app, but if you didn't, I just remind you. And the second, those who want to vote, you can still have a chance to vote for one of these nice presentations, which we will see just now. So we have uploaded about 15 poster previews, and I would like people to line up because they will be played in this order. P3, P5, P6, P9, P12, P13, P16, P17, P20, P22, P23, P24, P25, P26, P27, P30, and P31.
We should come first then.
should go.
It should go, yeah, normally. Yes. But there was some technical problem. He shouldn't announce the closing of the previous session.
Yeah, okay.
So that the audience will stay.
Yeah,
to be good.
So my name is Karl Koch, and I'm giving this introduction on behalf of Christoph Pilger, who is on parental leave. So we looked at the epicentral, or at the infrasound signals from the last DPRK event in September 2007 at IMS station 45, northeast of the test site. You find epicentral infrasound about 25 minutes after origin time, and this infrasound can be attributed to stratospheric and thermospheric returns. You also see, of course, seismic arrivals because the sensor is vibration sensitive, but there are precursor signals starting a few minutes before the epicentral infrasound, and a late arrival that comes in about 8 minutes after the epicentral infrasound. So this can be, the late arrival can be attributed to the cavity collapse of the associated with the explosion, and the precursory arrivals can be associated with strong ground motions along the in the epicentral region and along the path. So please come to my poster and I will give you more details.
Well, I'm presenting for Negaro and Greg Johnson. They are my colleague. I'm Chandan Saike, I'm not the author. Basically, results I'll be presenting on this poster is the yield of this particular bolide over Bering Sea. These data were analyzed. There are so many stations, and from there they got a predominant frequency period. From there, they used their relation to get what should be the yield from nuclear to chemical. Basically, they got the bolide, and their range of yield that they have got, which is much lower than 173, who was presented by Peter Brown and in the other talk, and also it's much lower. It goes from 4 to 34, but their height is about 25 kilometers. If you come, I'll be able to explain how these numbers were derived, much lower yield for this bolide. Thank you.
Hello. My name is Lilia Dimitrova. I'm from Bulgaria. Our poster presents a study of tectonics and glacier seismicity on Livingston Island, Antarctica. This study was carried out during the 3 years project on the Livingston, which carried out on the Livingston Island. During 3 summers, Antarctic summers, we installed a broadband seismic station near Bulgarian Antarctic base, and we recorded more than, for these 3 summers, recorded more than 12,000 events. Almost 300 of them are tectonic events, and another are ice-producing events. We applied a method for epicenter location on the base of 1 3-component seismic station, and produce and obtain very nice result. Thank you. Welcome to our poster.
Good afternoon. My name is Yasmin Hamid Shamkhi from Iraqi National Data Center. Through our use of IDC products, capacity building system, and from the benefit from NDC in a book software package, such as GeoTool, SciScom P3, DTK PMCC, we analyzed two events as example: an explosion in Ukrainian munition depot and the seismic event at the Iraq-Iran border. If you want any information of my poster, please come to visit my poster. Thank you very much.
Hello, I'm Rob Abbott. What you're looking at here are two borehole recordings of two explosions in the source physics experiment. The recordings were made on distributed fiber optic acoustic sensing sensors, and we have a high spatial sampling with a channel spacing of about 1 meter. What this allows us to do is to track continuous wave fields of P waves, S waves, damage, spall, reflections, mode conversions, and other things. This is unprecedented because before this data set existed, we had 4 channels instead of 400 channels to look at these effects. We also have some modeling in the natural units of strain rate to present as well. So please come by.
Okay, so I'm Ross Hayburn from the UK NDC. So in this poster, we take a look at how the effectiveness of 2 different methods of seismic source depth estimation, namely depth phase identification and inversions of surface wave amplitude spectra. We look at how the effectiveness depends on the focal mechanism. One of our observations is that even when the surface waves don't constrain the depth well, the focal mechanism is relatively stable in the inversion, and that can be a useful tool for helping guide the search for teleseismic depth phases. So if you want to find out more about the poster, please come down and have a chat.
Good afternoon. So we've been looking at the Galen tests recorded at Warramunga, Yellowknife, Estelle Muir, and the array at GBA. We've noticed that the waveform characteristics in the first 2 to 5 seconds seem to vary depending on the location across the test site. We believe this is to do with topography. And we tried to model this using a hybrid waveform modeling approach which couples a global wave propagation solver, AXISEM, to a 3D near source solver, WPP. So come by the poster and you can see whether we've been able to match some of these observations. Thank you.
Hello, good afternoon. S waves are a key distinguishing factor to distinguish explosions from earthquakes. To understand the generation of S waves, we deployed 1,000 geophones around a chemical explosion at the Nevada test site. We collected a lot of data, and it appears that S waves are primarily dominated by path effects. Thank you.
Hi, I'm Andrea. So our poster is on the application of seismic moment tensor to source type identification. We present a summary of our inversion results in different tectonic settings and at various distances from a few to 1,000 kilometers. And we also examine the use of 3D Earth models and wave propagation solvers in improving seismic source estimates. So please come by the poster tomorrow if you have any questions.
Good afternoon. The aim of this work was to create a new, reliable seismicity map of the Pannonian Basin. In this poster, we present the most accurate hypocenters so far in the study area. We created the initial locations with the iLoc algorithm. Then we used the baseloc multiple event location algorithm. We used several hundred of ground truth events to tie down the location pattern of the seismicity. And our solution is more accurate than the original locations. So if you have any questions or you're interested, please come by. Thank you.
Hi, I'm Scott Phillips, Los Alamos. We use coda-spectral ratios to study source effects and source models. This example is from the source physics experiment, which you've seen a couple examples from already. Very interesting results here is we find this notch, which is a surface wave effect near the source, within a kilometer of the source. Interestingly, it propagates out to regional distances. We believe scattering is the cause of this. Our regional S comes from, and P comes from scattering of near source surface waves. Thanks.
Good afternoon, I'm Cengiz Anik from Hungary. 2 years ago, we installed a new infrasound array in Hungary, which is co-located with a broadband seismological station. And together with another 30 seismological stations, we detect several seismoacoustic events. In this April, we published a bulletin containing all the identified and located seismoacoustic events. For further details, please come to my poster.
Okay, my poster is about two accidental explosions, one in here close to Vienna in December 2017, and the other one in September 2018 near Ingolstadt. The infrasound that we deal with is unusual, first of all, for the Austrian explosion in terms of the observational data, and for the Ingolstadt explosion concerning the modeling or forecasting results. The two explosions have been widely observed by the Alperae seismic network, showing strong seismoacoustic phases. I touch here only on the infrasound signals. For the Baumgarten, I'm dealing with large azimuth slowness deviations from the expected values. And for the Ingolstadt explosions, I'm dealing with infrasound signals that are hardly explained by the model. So this poster touches on our capability of how well we can model infrasound from specific events. Thank you.
Yeah, we are trying to understand the effect of sediments and the water layer actually. When we look at the data coming in from DPRK explosions to Japanese stations, we have lots of data coming in, so we have grouped the stations. So we have got dispersion curve for different groups. From there, we inverted the model. Then finally, we created synthetics by putting laterally weak transition zones and see how well we can fit the beginning part of the waveform, basically long period wave you will see. And we will not be fitting the late arriving surface waves, which are coming from all over, but in the beginning part of the seismograms, irrespective of where from they are coming, we have pretty good fit. We had to do Q structure. We had to put water layer thickness play with that. With all those things we played. And if you come to our poster, you will see which part of the waveform we have been able to model accurately. And eventually, after getting this model, we are going to look at the yield of these events in terms of reduced displacement potential functions. Thank you.
Good evening, I'm David Steedman from Los Alamos Lab. One more poster on the source physics experiment. I've used the data gathered near to the chemical explosion sources to develop a geomechanical response model that explains, possibly explains why there's excess shear developed due to a buried underground explosion. Then it's partly based on scaled depth of burial, and I mapped the scaled depths of burial of the 6 tests that we did at the granite site to the estimated scaled depths of burial of the 6 DPRK shots, and there seems to be one-to-one correspondence between developing shear near to our sources and the inability of far-field seismic measurements to distinguish between earthquakes and explosions from the DPRK events. Thank you.
So thank you very much to all presenters, and I think we will see each other tomorrow at 2:30 at your poster. Thank you very much. That concludes our session.
meeting that we assess research, assess the
Yeah.
compare or
Yeah, yeah.
something.
What we have to do tomorrow is actually to write a highlight.